This lesson deals with an audio frequency inverting amplifier. You can find these notes in the ECE202 ebook in Chapter 12, starting on page 11. Let's revisit the audio frequency inverting amplifier that we used to introduce the Bode plot concepts. Let's solve for V out over V in, and let's sketch the Bode plots. As we've shown before, for an inverting amplifier, the gain is minus Z2 over Z1. In this case, Z2 is just a resistor, R2, and then we have a series combination of R1 with a capacitor whose impedance is 1 over SC1. Multiply numerator and denominator by SC1, so I get minus SC1R2 over 1 plus SC1R1. C1 is 1 microfarad, R2 is 100K, and R1 is equal to 10K. That turns out to be a minus 0.1 times S over S times 0.01 plus 1. Let's pull out the 0.1 and the 0.01, and we're left with just S in the numerator, S in the denominator, and then 1 divided by 0.01 is 100. This ratio is equal to 10. So our transfer function in S is minus 10, S over S plus 100. When we do the Bode plots, we're looking at S equals J omega. Minus 10, J omega over J omega plus 100. Again, I'm going to make this look like our forms. The numerator is one of our terms, but the denominator isn't. So let's pull out 100 and make this a 1. So I have minus 10 divided by 100, then 1 plus J omega over 100. So write that as a product of three terms. This ratio, which is equal to a minus 1/10, times J omega, and then times 1 over 1 plus J omega over 100. This is a form 1, a form 2, and a form 5. Let's sketch the three terms. 20 log of the magnitude of the first term is 20 log of 1/10, which is going to be minus 20 dB. I've shown this here as a dashed line. The term J omega passes through 1 radian per second with a slope of 20 dB per decade. So here's 1 decade, and we've increased by 20. Another decade, we've increased by 20 more. Lastly, we have the form 5, which has an omega C of 100. So below 100, we have a slope of 0 dB per decade, and then above that, we have minus 20 dB per decade. And so 1 decade up, and we've dropped 20 dB. For the angles, I have J omega, which has an angle of 90 degrees. The minus sign here I could show as a plus 180 or a minus 180. I'll pick minus 180. And then lastly, the form 5, we're down 45 degrees at 100 radians per second. And then we're down 90 degrees at 1 decade higher. And then if you go 1 decade back, we're at 0. Now I want to add up all the curves. We can do that by identifying regions where the slopes are constant for each of the forms that we're graphing. So here I have a slope of plus 20, 0, 0 dB per decade. So the sum is going to be 20 dB per decade. Now I try to pick some easy point to start my sketch out. Looks like I did it here at 0.1. Value is 0, minus 20, and then minus 20 again. So the sum is equal to minus 40. Then 1 decade, increase by 20, increase again, and increase again. In the second region, I have a slope of plus 20, now a slope of minus 20, and a slope of 0. The sum of the slopes is 0, so we just level out. What I'm going to do from now on is to sketch the forms as dotted lines, and the summation as a solid line. So just do it on one graph. Now, normally we don't work in radians per second in lab. Our equipment's calibrated in hertz, and so we could redo this scale by just dividing by 2 pi. So 100 radians per second divided by 2 pi is 15.9. You could also just use that scale here initially if you wanted to, and pull out a 2 pi from the term that we have in our forms, in this case form 5. Now we do the same thing for the angle, but all we've got here is really the sum of two scalars added to our form 5. We add plus 90 and minus 180, you get minus 90. You're just going to add a constant to this. It's going to shift it down. So the whole curve moves down 90 degrees. So we start out at minus 90, and then we drop eventually to minus 180. The reason I picked the minus 180 instead of the plus 180 was so that my final answer would fit between plus and minus 180, if it's possible. We can also do some interpretation of our schematic, our Bode plot, and also our transfer function. So let me go back to the schematic. Let's take a look at what this circuit does as frequency increases. Suppose that the frequency is high enough that this capacitor's impedance is much, much smaller than the 10K ohms that's here. In a sense, this would look like a short circuit. And the gain would then be approaching minus 100K over 10K, which is a gain of minus 10. In our transfer function, we actually see the same thing. When the magnitude of S gets larger and larger, the denominator is dominated by S compared to the 100. So this equation is approaching minus 10 S over S, which is a gain of minus 10. Screw down to the Bode plot. We see the same thing. As the frequency gets high enough, we eventually approach a gain of 20 dB, which is a gain of 10, and we're approaching an angle of minus 180 degrees, so a gain of minus 10. Let's go the other direction. As the frequency gets lower and lower, we approach an angle of minus 90 degrees. Also, this is decreasing as we decrease frequency. In other words, it's changing at a rate of 20 dB per decade. And where's it heading towards? Minus infinity dB. 20 log of 0 is minus infinity. So the gain is approaching 0, and the angle is approaching minus 90. Let's see if the circuit and the transfer function are saying the same thing. So I'll scroll back up. In the circuit, as the frequency gets lower and lower, this becomes a much larger impedance than this. So the gain is approaching Z2, which is 100K, divided by a very large number, really tending towards infinity. So the gain is approaching 0. What about the angle? As the frequency is getting lower and lower, the impedance of this element again is getting larger and larger. And what I've got is Vn is across these two elements because of the 0 volts that's here. You can think of it as a voltage divider. If you have this impedance divided by this plus this times Vn would be the voltage across these two elements, and then what's across here would be a very large number divided by R1 plus a very large number. So most of the voltage is right across here as the frequency gets lower and lower. Let's assume that Vn has an angle of 0. Remember in chapter 8 we talked about Eli the Iceman. Sketch my imaginary axis and my real axis. So I've got a voltage V across the capacitor. The current would be over here, 90 degrees ahead of it. Our trick to remember this is IC, and then thinking of voltage in the early days of electrical engineering as the letter E. The voltage across here has a magnitude of Vn, an angle of 0. Then the current that's flowing in here has an angle of plus 90 degrees. But that current's going to flow into this resistor, going to create a drop, and the voltage out is going to be the negative of this voltage plus 0. I get a minus sign from that, and I get a plus 90 degrees from this. The overall angle then would be minus 180 plus 90 or minus 90. The circuit's also tending towards a gain of 0 and a phase angle of minus 90. Let's look at the transfer function. As the frequency gets lower and lower, this term becomes smaller and smaller. So we approach minus 10 s over 100, which is minus 1/10 times s. S is equal to j omega, so that's plus 90 degrees. And then the minus sign you can think of as, again, minus 180 or plus 180. And we're approaching either minus 90 or plus 270. So we're seeing that the circuit, the transfer function, and the Bode plot are saying the same things, but in different forms. All of this is on the next page. Look at one more idea. We said that the transfer function has a pole at s equals minus 100 radians per second and a 0 at s equals 0. What does that mean in terms of the circuit? Well, let's let s equal minus 100. So what's the term that has an s in it? Just the capacitor's impedance. So it's 1 over SC1. So minus 100, and the capacitor was 1 microfarad. That turns out to be minus 10K. If we put that value in for the capacitor, what you've got is a series combination of minus 10K plus 10K, which is equal to 0. So our transfer function for this algebraic evaluation is minus R2 over Z1, but Z1 is equal to 0. So the gain approaches infinity. So a 0 of Z1 is a pole of the transfer function. What about s equals 0? Let's do the same thing. Plug in s equals 0, then you have 1 over 0 times 10 to the minus 6th, and that's equal to infinity. So it looks like an open circuit. Total impedance then is infinity plus 10K, or just infinity. So our gain then is minus R2 over Z1, minus R2 over a very large number, and so our gain is going to approach 0. Pole of Z1 is a 0 of our transfer function. Now what happens in our forms when we have internal critical frequencies? In other words, things that are not at s equals 0 or s equals infinity. Like in this last case, we had something at s equals minus 100. Well, the magnitude of our real poles and zeros corresponds to our break frequencies, or what we call critical frequencies. For internal critical frequencies, when a real pole is encountered, the slope of the composite magnitude Bode plot decreases by 20 dB per decade. The reason for this is that a pole is a form 5. We go from 0 dB per decade below omega c, and then as we pass through omega c, the slope changes to minus 20 dB per decade. We see a net decrease. In the example on page 11, the slope was going from plus 20 dB per decade for frequencies below 15.9 Hertz, and then it decreased to 0 dB per decade once we hit 15.9 Hertz. When encountering a real 0, the slope of the composite curve increases by 20 dB per decade because we're hitting a form 4. 0 dB per decade below omega c, and then above that, plus 20 dB per decade. Now we are dealing with AC circuits, and S is equal to j omega and cannot be a negative real number. So the real poles and the real zeros are only algebraic consequences of the form of the transfer function. But these can be interpreted. Lastly, to again reiterate, all of the above in the previous pages are pointing to the fact that the circuit, the Bode plots, and the transfer function are all equivalent. Each is highlighting some form of information. Let's verify our results using PSpice. So I'll create a splice file for my circuit. Need a title, call this Audio Frequency Inverting Amplifier. and a dot end, dot probe to sketch all of my variables, and then I'm going to plot my frequency response, say from 1/10 of a hertz to 10 kilohertz. That's actually 5 decades. So if I do 40 points per decade, I'll get 200 points on the screen. I'll let you look back at the original schematic, but I number the nodes 1 through 4. The voltage source is between nodes 1 and 0. It's going to be an AC source with a magnitude of 1 and angle of 0. C1 was between 1 and 2, 1 microfarad. R1 between 2 and 3, 10K. R2 between 3 and 4 is 100K. And our voltage control voltage source, the plus terminal was at the output node 4. The ground was the negative terminal. And then we're sensing from the plus node to the minus node. The plus node is grounded and the minus node is node 3. And we're giving it a very large gain of 100 million. And the dark line here is my response. Now our asymptotes had a change in slope at 15.9 hertz. And so I have to figure out where is that on this scale. Now if you measure this distance, it's about 1.1 inch. I'm going to go back between 1 and 10 and then take the log of the value that I'm interested in and just scale back between 1 and 10. That would be our 15.9 is 1.59. That turned out to be 0.201. The width here between 1 and 10 is 1.1 inch, and so I'll multiply that by 0.201, and the value of 15.9 is 0.221 inches from the value of 10. The actual value of gain was 16.993 at this frequency. This is the nearest point I had with the 200 points I sketched, and I'm down 3 dB from my gain of 20 dB. Our worst error is right here, where the asymptotes come together and the actual curve is smooth. It's called an audio frequency inverting amplifier because we're letting all the signals pass above 15.9 hertz, and the audio band is roughly from 20 hertz to 20 kilohertz. Now this appears to have gain that continues on forever, but we'll see in later courses like ECE202 that the gain actually comes down at higher frequencies due to the non-ideal bandwidth of the op-amp. Last, let's take a look at the phase angle. The phase angle of my transfer function is the phase angle of the output voltage minus the phase angle of the input voltage. But the phase angle of the input voltage is 0. So just the phase angle of the output node voltage, V4, is the phase response of my transfer function. And you can see it goes from minus 90 to minus 180. And then I again use my technique of being able to make my own log paper and found the frequency 159. Again, that's 0.221 inches from here. And likewise doing the same thing. I then connected these 2 points up, and I'm changing at a slope of minus 45 degrees per decade. And you can see here I've got my worst error at these 2 frequencies. The error is about 5.7 degrees. At the 45 degree point of our form 5, that's occurring at 15.98 hertz, and we're calculating that to be 15.9. We're pretty much within the default accuracy of the SPICE program. One last thing to say about the audio frequency inverting amplifier is that it's an example of a first order high pass filter. And the general form is some constant times S over S plus alpha. And these are some of the properties of the audio frequency inverting amplifier.